Yes, all of you can see my screen now?
Yes, ma'am.
Okay. So once I finish today's class, I have been sending you these PPTs in parts, okay? Once I finish today's class, I'll send the entire PPT together so that you get the entire, the first chapter of your quantum mechanics syllabus that includes all the initial introductory ideas, basic ideas in one PPT. So once I finish today's class, I'll upload this PPT as a whole in your LMS. Till now, I have been uploading parts of this. After this, I'll upload the thing as a whole. And the note on this, not the slides, the written part, the written note has already been uploaded in the LMS. That entire thing is there. So that you can download. Okay. Okay. So we I discussed operators in my last class, and so quickly I'll go through the concept of operators, and then we'll discuss the rest of it. So what happened? Okay, so as I told you, we all know what is an operator. Any operation that changes a particular function is called an operator. So this is an example. And we also discussed that if an operator is such that when it operates on a function, the function remains unchanged except for a multiplicative constant, then such an operation is called an eigen operation, and such an equation is called an eigenvalue equation. Okay, where if a particular function satisfies the eigenvalue equation, then it is called the eigenfunction of the operator O, and lambda, the related constant, is called the eigenvalue of O belonging to the eigenfunction fx. All right. In German, the word eigen means characteristics. We discussed eigen operations and eigenvalue equations in some detail in the last online class that we had. So this is just to, so that you can just remember what we are talking about. Now, the one-dimensional wave function is of this form. We have done this several times now. And if you take the first derivative of this function with respect to x, okay, then this is what you get. I by h cut p psi, where p is the linear momentum in the x direction. So we can write p in this manner, and therefore p, you see we have psi both on the left hand side and the right hand side. So we can say that p is represented by this differential operator minus I h cut del del x. All right. Similarly, if you take the first derivative with respect to time of the wave function psi, then you get something like this. And once again, we can say that we can represent the total energy E by an operator like this, a differential operator IH cut del del T. Okay. So you see, P and E are two known dynamical variables which can be represented in the form of differential operators. One in terms of x and the other in terms of t. So in quantum mechanics, basically, dynamical variables like linear momentum, total energy, etc. can be represented by linear differential operators, and if we do so, this equation can be written in the form operator P acting on psi gives you P into psi. This can be written in the form operator E acting on psi gives you E into psi. Okay, just remember that there is a subtle difference between P operator and P just by itself. This is P operator is minus IH cut del del x. This P is just the value of the linear momentum in the x direction. E operator is IH ka del del t. This E is just the scalar value of the total energy. These are values, okay? P and E here are values, whereas P hat and E hat are operators. So don't get confused with this notation. Whenever we put hat on the top of a letter, of a symbol, it means it is representing the differential operator and not the absolute value. Whereas when we are not putting the hat, it means it is the absolute value of the given symbol, the parameter. Okay. Now, as you can see that these two equations, P operator acting on psi giving P psi, so the function doesn't change. Again here the function doesn't change. These are nothing but eigenvalue equations. And so we can generally write that in quantum mechanics, all dynamical variables can be represented by operators, and all operators have eigenfunctions and corresponding eigenvalues. Okay. So we can now make a general statement that operators in quantum mechanics are eigenoperators. For example, linear momentum, we already saw how linear momentum can be represented as an operator and how it satisfies an eigen value equation, right? Similarly, so we can write this statement now. This is how it reads. Psi is the eigenfunction for the operator Px hat equal to minus IH cut del del x with the eigenvalue Px. Okay. Kinetic energy. We've got del del x. Now you take the second derivative del 2 psi del x2 and this is what we get. So the kinetic energy can be represented by the operator minus h cut square by 2m del 2 del x2. And so we can write k hat psi equal to k psi. Okay, so this is the eigenvalue equation and we can write that psi is an eigenfunction for the operator kinetic energy with the eigenvalue of the total kinetic energy. Next we talk about the total energy. Okay. So we know that for non-relativistic one-dimensional motion, this is the total energy, px square by 2m plus v, where the particle is moving under the action of a potential v. For a free particle, of course, v is 0. But we already saw that px square by 2m is minus h cut square by 2m del 2 del x2. So we can write E psi equal to minus h cut square by 2m del 2 del x2 plus v operating on psi, right? So E is this operator which is often written as capital H, okay? Since we are working in one dimension in the x direction, so in this particular case, we are writing H suffix x. H is the total energy operator, or more popularly known as the Hamiltonian operator. Okay, so the total energy is also called the Hamiltonian operator and one of the most important functions in the realm of quantum mechanics, statistical mechanics. In your future higher semesters, when you study the more higher and more complex topics of physics, you will see that in most of the problems, the first thing that you need to do is write down the Hamiltonian, okay, and then solve the problem. So this is the Hamiltonian operator. In 3 dimensions, of course, H is this, that is del 2 del x2 is replaced by the Laplacian operator. So the corresponding eigenvalue equation becomes H psi equal to E psi. All right. Now you see this equation here, E psi equal to minus h cut square by 2m del 2 del x2 plus v whole operating on psi. This is nothing but Schrodinger equation. If you can recall and if you can recognize, then this is nothing but Schrodinger equation. So basically, the solutions of the time-independent Schrodinger equation are the eigenfunctions of the Hamiltonian operator, and the eigenvalues E are the only possible values of the total energy that the system can have. This is a very, very important statement. So please note this down very carefully. Once again, I'll just repeat what I said. The solutions, see this equation is basically boiling down to a compact form where we write H psi equal to E psi. So psi, which are the solution of Schrodinger equation, is an eigenfunction of the Hamiltonian operator with the eigenvalue of E, which is the total energy. So we can now say that the solutions of the time-independent Schrodinger equation are eigenfunctions of the Hamiltonian operator. And since this is an eigenvalue equation, therefore, these values of energy E are the only possible values of total energy that the particle or the system can have. It cannot have any other value of energy which will not satisfy this eigenvalue equation. Okay, so this is a very, very important and comprehensive statement that we are making here about the total energy and the Hamiltonian operator. Next comes angular momentum. You know what is the formula of angular momentum, and you can write it down in terms of the components. Therefore, the different components are in this form: Lx, Ly, and Lz. And using the operator form of the linear momentum in the three directions px, py, and pz, we can write expressions for the three components of the angular momentum operator. So we have the three angular momentum operator Lx, Ly, and Lz in terms of the linear momentum operators in the three directions x, y, and z. Okay. If you recall the expression of expectation value, remember what was expectation, what was the definition of expectation value? I told you that quantum mechanics is a predictive study. We are no longer in the realm of deterministic discussions. Everything here is stochastic. So we cannot say that this is exactly what is happening. We can just predict that this may happen. The probability of this happening is so and so. The probability of finding the particle in this particular position is so and so. So all we are talking about are in terms of probabilities. Okay, there is no certainty anymore. Everything is predictive and probabilistic, and therefore the definition of expectation value becomes very important. How did we define expectation value? We said that if we observe one particular system which is represented by the wave function psi is observed by several probes at a particular instant of time, and the result of all these observations are taken and we take the average of it, then that is known as the expectation value. So this is how we defined the expectation value of a given function fx. This angular bracket and within it fx represents the expectation value, and its mathematical formula is this: integration minus infinity to plus infinity psi star f psi dx in one dimension, that is when we are considering only the x direction. In 3 dimensions, of course, this will be r, x will be replaced by r, and dx will be represented by d tau, the infinitesimal volume. So this is the definition of expectation value. Okay. So using the operators, we can write down the corresponding expectation values of the dynamical variables. For example, expectation value of x is this. In place of fx, we write x. Okay, so minus infinity to plus infinity, psi star x psi dx. If the form of psi is given, you can easily calculate this value. Expectation of potential, minus infinity to plus infinity psi star v psi dx. Given the expression of potential and the expression of psi, after you solve Schrodinger equation, you can easily find the expectation value of potential. Expectation value of linear momentum in x direction, psi star px psi. So in place of px, you write minus ih cos del del x. So again, once you have the form of psi, you can easily calculate this and find out the expectation value of linear momentum. Similarly, expectation value of kinetic energy. In place of kinetic energy, you write down the operator form. So basically, you have to calculate del 2 del x2 acting on psi and then calculate this integration and you'll find the expectation value of kinetic energy. So in this manner, whatever dynamic variable you are talking about, you can calculate its expectation value by writing down it in the operator form. Now we have to talk about the limitations of the wave function psi. That is, if we have a particular function psi and someone asks you, is this a possible solution of Schrodinger equation? Then how will you decide whether it is really a possible solution of Schrodinger equation or not? Okay, so this is a very, very important concept. So psi, it must be first of all in accordance with Born interpretation. So psi must be such a function that psi star psi always represents the probability density. Remember, we had discussed all this in great detail that even if psi, even though psi is a complex function, but still even though psi is a complex function, but still it does make sense because from Born interpretation we get a physical sort of physical feeling about what psi represents, because the moment we take psi star psi, then that is a real function and that gives us the probability density, the probability of finding the particle at within a given interval. Okay, so whatever be the form of psi, it must be in accordance with Born interpretation, and it must have a functional form that is an allowed solution of Schrodinger equation. Okay, so what are the what should I say? What are the restrictions on psi? The following are the restrictions. Psi must be finite. So whatever form it has, it cannot blow up at minus or plus infinity. Del psi del x must be finite. This is the first condition. Psi must be single valued. Del psi del x must be single valued, which means that at a given x, psi can have only one value. It cannot have multiple values for a given x. And the same is the case with its first derivative del psi del x. And psi must be continuous. Del psi del x must be continuous. Okay, so these three are the mandatory conditions that must be satisfied by a function psi so that it may be a possible solution of Schrodinger equation representing a particular particle. A function that satisfies the above conditions is called a well-behaved function. Okay, please remember these three conditions very well, because when we are going to solve Schrodinger equation under different conditions, these are the conditions that will give us the boundary conditions. Okay, so using these we will find out the different constants. You will get to know what I'm talking about once we do the problems, uh, rather than talking in this abstract manner. But for the time being, just remember that these three conditions are a must for the function to be treated as an allowed solution of Schrodinger equation. That is, the function must be well behaved, finite, single valued, continuous. Three basic criteria. Psi and its first derivative must be finite, single valued, continuous. Okay? And as I told you, these conditions will serve as the boundary conditions for determining the wave function when we solve Schrodinger equation under different circumstances. Next comes the normalization of the wave function psi. Okay. When you get the solution, or when you solve Schrodinger equation and get a possible value of psi, a possible expression for psi, the first thing that you do is test whether it is a well-behaved function. When it passes that test, when you are satisfied that yes, this is a well-behaved function and it can be an allowed solution of Schrodinger equation, the next thing that you need to do is normalize the function. What does that mean? Psi star psi. It means the probability of finding the particle between x and x plus dx. We discussed Born interpretation in some detail. Okay, so in 3D, this becomes psi star psi d tau. So psi star psi dx is the probability of finding the particle between x and x plus dx. Psi star psi d tau is the probability of finding the particle between a volume tau and tau plus d tau. Okay. Now the total probability that the particle will be somewhere in space at any given instant of time t is this. This psi star psi d tau is the probability of it existing within an infinitesimal volume d tau. So the probability of it existing somewhere in space has to be the integration of that function into d tau. So this is the result, the probability that the particle exists somewhere in the three-dimensional space available. But the particle has to be somewhere. I mean, if you are talking about a particle, then it has to be somewhere between minus infinity and plus infinity at a particular instant, right? Which means that this total integration must be equal to 1. Okay, have you understood this? Why this equal to 1, or do you want me to repeat once more? If you want me to repeat it once more, then please unmute and tell me. It's all right. You've understood why the integration is equal to 1. Hello, can you all hear me?
Yes, ma'am.
Okay. So, I mean, you have to understand, okay? So, suppose, okay, let me give you an example. Suppose I tell you that say I tell you, I just tell one of you that go to the physics lab and bring a duster. All right? The duster is in a box. All right? So you go to the physics lab and you see that there are several boxes, and you don't know in which box you will be able to find the duster. Okay, so you start opening all the boxes. Now the probability that you will find the duster in one of the boxes is not known. You don't know whether the moment you open one particular box you will get the duster or not. Correct? That you don't know. You might get the duster or you might not get the duster. But if there are 10 boxes and I have told you that the duster is in a box, if there are 10 boxes, then the probability that you will get the duster in at least one of the 10 boxes, that is for sure. you might not know in which particular box you will get the duster. So you will not go, the situation is not like this, that you will go open a box and take out the duster. For example, there are 5 boxes, each of different color. And I tell you that go find, bring the duster is in the blue colored box. Then the thing becomes very easy. I have told you with certainty that the duster is in the blue colored box. You go there, you don't even look at the other boxes, just straight away take the blue box, open it, you find the duster there. This is one scenario. This is classical physics. When we are in quantum physics, I just tell you that go find the duster, it is in one of the boxes. So you don't know which box to open. You have to open each box and see whether the duster is in there or not. Okay. And after you have opened all the 5 boxes, maybe you will find the duster in the very first box. Maybe you will find the duster in the third box after opening it. Maybe you will find the duster after opening all 5 boxes. We don't know. There is no certainty. This is quantum mechanics. However, the probability that you will find the duster at least in one of the 5 boxes, that is for sure. Okay. So when you integrate over all the 5 boxes, that probability density has to be equal to 1, because the duster has to be somewhere within the 5 boxes. Now is it clear what I am talking about when I say the particle has to be somewhere within space at any given instant, and why this integration is equal to 1? Is it clear? Come on, someone please unmute and tell me, I can't see you all.
Yes, ma'am.
Yes, ma'am.
Okay. Okay. So this is why the total integration from minus infinity to plus infinity of the probability density is equal to 1. In one dimension, we will replace d tau by dx. In 3 dimensions, we use the volume. So a wave function which satisfies this condition is said to be normalized to unity. You understand why it satisfies this equation, and when it does satisfy this equation, it is said to be normalized to unity. Okay? So in one dimension, this is the normalization condition. So minus infinity to plus infinity, psi star psi dx equal to 1 is the normalization condition of the wave function in one dimension, and minus infinity to plus infinity, psi star psi d tau equal to 1 is the normalization condition in 3 dimensions. Okay. Now, that is the normalization condition. So what do we do when we get a particular solution? So say psi, we know that the general solution, the general expression of psi, the solution of Schrodinger equation is this. Again, we have discussed this in detail. Okay. So its complex conjugate will be this. If the function is Cn psi n e to the power minus I by h cut ent, then the complex conjugate is C star psi star e to the power plus I by h cut ent. Okay. So from the normalization condition, integration psi star psi equal to 1, we can write the expressions for psi star and psi using this, and this is the condition that we get. Okay. Cn star Cn integration minus infinity to plus infinity psi n star psi n dx, plus these are for conditions where both the solutions belong to the same integer n. But it might not always be the case. There will be cross terms also. Okay. And then the second term arises. We have a double summation, summation over n, Cm star e to the power minus I h cut emt, Cn e to the power plus I by h cut ent, integration psi m star psi n dx equal to 1. Okay, but life is not as complicated as this expression looks like. You might think that what are these expressions ma'am has written? How are we going to solve these? We will soon see in the next slide that wave functions are mutually orthogonal. What does that mean? It means that psi n star psi n dx is 0. That is, when m not equal to n, then this integration becomes 0. Okay? Whereas psi n star psi n equal to 1 if m equal to n. This is the meaning of mutually orthogonal functions. In more simple terms, psi m star psi n dx integration is equal to a delta function. It is equal to 1 when m equal to n. It is equal to 0 when m not equal to n. Therefore, as soon as we know this, that the functions are mutually orthogonal, so we can quickly write this term as equal to 0 because here m not equal to n. So we are left with this term to be equal to 1, and therefore Cn star Cn equal to 1. So if in this expression of normalization condition, this term goes to 0, so the entire second term goes to 0. This term is equal to 1. So what we are left with, summation over n Cn star Cn equal to 1. So this is the normalization condition. Clear? I hope this is not very difficult to understand. The only thing you have to keep in mind is that the functions are mutually orthogonal. Next, we talk about the stationary states. These are all sequential. You know, it all comes as one comes as a consequence of the other. Operator, eigenvalues, probability density, normalization condition, and now stationary states. Okay. Again, we know general expression of the general solution of psi is this, and therefore by definition the probability density psi star psi is written in this manner. The same thing as we wrote for normalization condition. Okay. Now you see that in general the probability density is time dependent. There is no integration over here, so there is no way in which you can impose the condition of mutual orthogonality. If we could impose the condition of mutual orthogonality, then the second term would become 0. But here there is no integration. It is only summation. So you cannot do that. So in general, we see that the expression of probability density is time dependent. The expression of time comes out explicitly in this form. Now we consider a condition where all constants are 0 for n not equal to k and non-zero when n equal to k. In other words, we are talking about a particular solution where the solution exists only for a particular energy value Ek. Not all energy values are allowed. Only particular values of energy given by Ek are allowed. So Cn, the constant, is 0 for any n which is not equal to k and is non-zero for any n which is equal to k. So for this particular energy k, the particular solution is given by this. Instead of summation here, summation was for all n. Now we know that solution exists only for one n which is equal to k. So we do away with the summation sign and we write psi is equal to ck psi k e to the power minus h cut ekt. And then the probability density becomes ck star ck psi star psi k, because minus I by h cut ekt and its complex conjugate plus I by h cut ekt, they cancel each other out, and therefore the probability density becomes time independent. Okay, So we can write that for a particular solution, the probability density does not evolve in time, and such states are called stationary states. So if you are dealing with a particular solution, which will be the case when you deal with specific problems, then you can clearly say that a given particular state does not evolve in time and the probability density is time independent, and therefore such states are called stationary states. Okay, again a very important basic concept. What are stationary states? Okay, now these questions come in the exam. What do you mean by stationary states? Please don't Google your answers. Please try to understand the thing, why it is stationary state. Stationary because there is no change with time. Time might change, but the function will not change, which is why it is a stationary state. Okay, and then you can look up the derivation from a book or from this my note or from this PPT, wherever you want to get it from. But please don't Google your answers and write, things which you don't understand, and therefore you don't know whether they are correct or not. Next comes orthogonality of eigenfunctions. As I told you, eigenfunctions are mutually orthogonal, and now we'll see that they are indeed mutually orthogonal. So if you consider normalized wave functions such that psi m is a function belonging to energy eigenvalue Em, and psi n is a function belonging to energy eigenvalue En. Okay, so you can, I hope you can recognize the eigenvalue equations that are satisfied here. H, capital H, Hamiltonian, H psi m equal to Em psi m, H psi n equal to En psi n. Okay, so then you can see that they follow that psi m star psi n integration minus infinity to plus infinity is equal to minus infinity to plus infinity psi m psi n star theta equal to 0 if m not equal to n, and equal to 1 if m equal to n. Okay, so in other words, psi m star psi n d tau equal to the Kronecker delta delta mn, which is 1 if m equal to n and which is 0 for m not equal to n. So if you consider the matrix over here, only the diagonal elements are present. All other elements are absent. Okay, only the diagonal elements are present and their values are all 1. This is the orthogonality or the orthonormality condition of the solutions of Schrodinger equation. We say that any two wave functions are orthogonal to each other. Now, the proof of this is given in my notes. It's a long proof, basically algebra, so I have not included it in the slide. You can look up and you won't find it difficult. All the steps are given. But it's just mathematics, which is why I did not include it here. But you need to understand the significance. Okay, why two wave functions are orthogonal. If you can recall your vector analysis classes, remember we said that if we have, say, n vectors, and these n vectors can be written as a linear combination of each other, then the vectors are not independent. When vectors are not independent, what is the difficulty? The difficulty is that you cannot write one in terms of the other two. Okay. For example, the Cartesian coordinate axis, x cap, y cap, j cap, they are mutually orthogonal, and you cannot write x or I in terms of j and k, or j in terms of I and k, or k in terms of I and j. Okay, not possible. So they are mutually orthogonal and therefore they are independent of each other. So wave functions belonging to different eigenvalues are independent of one another. A wave function belonging to an eigenvalue Em will not in any way interfere with the wave function belonging to a different eigenvalue En, which is why we have discrete energy levels in quantum mechanical system. There is no interaction between the states. They are independent of each other, which is why they satisfy the condition of orthogonality or orthonormality. Okay, this is a very, very important concept. Don't learn up by heart. Try to understand why this is happening, and then it will be easy for you to remember. And finally, we are going to talk about degeneracy, another concept that is important, and we'll talk in general now, and then we'll later on we'll have an example to show what this means. Suppose we have the eigenvalue equations h psi n equal to e psi n and h psi m equal to e psi m. Note that I have not given a suffix to e. I have not written en or em. So in both the cases, the eigenvalue equations are satisfied by the same eigenvalue e. Psi n is an eigenfunction of h with an energy value e. Psi m is an eigenfunction of h with energy value e. So what do we see here? We see that there are two eigenfunctions psi n and psi m of the Hamiltonian operator, both of which correspond to the same eigenenergy value E. They are different states and therefore of course they are mutually orthogonal, they are independent of each other, but they satisfy the eigenvalue equation with the Hamiltonian operator with the same energy value E. Then such energy is called a degenerate energy state. Definition: if two or more linearly independent eigenfunctions belong to the same eigenvalue, then the eigenvalue is called degenerate. Okay? For k eigenfunctions belonging to the same eigenvalue, it is said to be k-fold degenerate. Okay? For k eigenfunctions belonging to the same eigenvalue, it is said to be k-fold degenerate. Very, very important. Degeneracy, this concept is very important. You must note that any linear combination of degenerate eigenfunctions is also an eigenfunction belonging to the same eigenvalue. That is, if psi 1, psi 2, psi 3, etc. up to psi k say are linearly independent eigenfunctions for an eigenvalue E, that is, they all satisfy this particular eigenvalue equation with the same eigenvalue E, okay, then a linear combination of these functions is also an eigenfunction belonging to the same eigenvalue E. Have all of you understood this? So basically, to put it more simply, say h psi 1 equal to e psi 1, h psi 2 equal to e psi 2, h psi 3 equal to e psi 3, and so on. Say till psi 5, h psi 5 equal to e psi 5. So psi 1, psi 2, psi 3, psi 4 and psi 5, all of them are eigenfunctions of H with the same energy value E. Okay, then a function psi, which is a linear combination of these five functions psi1, psi2, psi3, psi4 and psi5 is also an eigenfunction of H with the same eigenvalue E. Alright, so although they are linearly independent states and they each satisfy the eigenvalue equation separately, but when you take a linear combination of them, then they also satisfy the same eigenvalue equation with the same value E. Alright, so this is the concept of degeneracy. Finally, we are now at a stage to summarize the postulates of quantum mechanics. Again, very important. It may come as a question to what are the postulates of quantum mechanics. So what I'm going to say now in the next two slides is basically the summary of what we have been studying, what we have been discussing in this portion from day one of our semester. First, any particle moving non-relativistically in a conservative force field can be associated with a wave function which will describe the behavior of the system in compliance with Heisenberg's uncertainty principle. This is almost de Broglie hypothesis. Okay, so with every moving particle, non-relativistically moving particle, we can associate a wave. The wave is formed by the superposition of several waves and it satisfies Heisenberg's uncertainty principle. For every observable dynamical quantity like position, momentum, angular momentum, total energy, etc., there is a corresponding operator. And all such operators are eigenoperators associated with particular eigenfunctions and eigenvalues. We saw this thing in today's class itself, that every observable can be represented by an operator, and that operator is an eigenoperator with a particular eigenfunction and a particular eigenvalue. Second postulate. So these are the some of the dynamical variables like position, potential, momenta, kinetic energy, total energy. There will be angular momentum, etc. And position operators, and you know the corresponding eigenvalue equations, x psi equal to x psi, potential, momenta, okay, the three momenta in the three directions separately and in three-dimensional 2 minus I h cut gradient. Kinetic energy in three dimensions minus h cut square by 2m del square. Total energy minus h cut square by 2m del square plus v or minus I h cut del t. So all the dynamical variables are representable in some or the other form of an operator, a differential operator. In three dimensions, the Schrödinger equation is obtained by equating the two operator expressions of total energy. Okay, so how do you write down the easiest way of writing down Schrödinger equation? If you suppose initially there is some difficulty in remembering Schrödinger equation. What is Schrödinger equation? You cannot write it down straight away. The best way is to write down the two forms of the total energy. One is minus h cut square by 2m del 2 plus v and the other is I h cut del t. And equate the two. Both are the expressions of total energy. So you can equate the two operating on psi. And that will give you Schrödinger equation. Next, the wave function must be a well-behaved function. What are the conditions of being a well-behaved function? Finite, continuous, and single-valued. Psi and its first derivative in space must be finite, continuous, and single-valued. Wave function is complex and therefore an abstract quantity. So function must be such that it always abides by the condition of Born interpretation. That is, psi star psi, the real value, must represent the probability density. And since the probability density, the probability of finding the particle somewhere has to be 1, therefore we have the condition in integration minus infinity to plus infinity psi star psi deta equal to 1. The average or expectation value of any quantity O is given by minus infinity to plus infinity integration psi star O psi deta. Okay. So if you see the last 2 slides of this presentation, postulates of quantum mechanics, I'll just go through them once more. Wave associated with a particle, de Broglie hypothesis, in accordance with Heisenberg's uncertainty principle. Every observable can be associated with a differential operator. Okay, and these are the operators for some known observables, for some often used observables. Second postulate. You write down the operator form of the total energy and equate them to get Schrodinger equation in 3 dimensions. Any solution of Schrodinger equation must be a well-behaved function that is finite, single-valued, and continuous. Wave function must be such that it is in accordance with Born interpretation of the fact that its complex conjugate and itself multiplied together, integrated from minus infinity to plus infinity, equal to 1, which is giving us the normalization condition. And finally, for any observable O, the expectation value is given by minus infinity to plus infinity f O, psi star O psi deta. Okay, so that summarizes the basic concepts of quantum mechanics that you need to know before you start solving problems. And I would expect all of you to please go through this PPT very well so that you are more or less thorough with these basic concepts when we start solving Schrodinger equation for different conditions. Okay, so in our next class, from our next class onwards, we'll do the problems that are given in your syllabus, and for that you need to know these postulates. You just go through the postulate, and for each thing you go back to the slide and go through it. You go through the notes. These are basic concepts, very important, and so